Hi everybody, this is our lab video. I want to take you through the labs, the guided activity this week through recording. I'm going to try and do that every week that I manage to have time to do, because I've heard feedback that this is helpful for some of you. So let's go. The aim of this lab, in this lab you will practice solving problems using the normal distribution. The focus will be on the use of distributions to put data into context. You will also practice to communicate data-based recommendations without using statistical jargon. I highly recommend watching the lecture videos or reading the assigned book pages prior to attempting to do the exercise in this lab. If you simply try to use the key to guide you or just stalking here to guide you, you might get stuck with some concepts that I've worked through kind of calmly through the lab. So make sure you start there. If you haven't, stop here, go watch the videos, only 3 this time, and then come back for the labs, okay? All right, so for those of you who have watched it, I'm here on the RStudio environment. Is that true, what I'm saying? It's not true. Let me get into the RStudio environment because I want to work from here to make sure everything is working well and not being weird. And I know I made this mistake before. I'll work using the key file so that we can work together to figure things out, and I won't write over the one that should be empty. All right, solving problems with the normal distribution. Triathlon times. In triathlons, it is common, here you go, I'll keep fixing errors, for racers to be placed into age and gender groups. Friends Leo and Mary both completed the Hermosa Beach Triathlon, where Leo completed in the men ages 30 to 34 group, while Mary completed in the women ages 25 to 29 group. Leo completed the race in 1 hour, 22 minutes and 22 seconds. That's 4,948 seconds, while Mary completed the race in 5,013 seconds. Obviously, Leo finished faster if we consider raw scores, right? But they are curious about how they did within their respective groups, right? They come to you for help as the data analyst expert. So question 1, I apologize that number. What information would you need about the performance of their respective groups to help them figure out who did relatively better? So what information would you need about the performance of their respective groups to help Mary and Leo figure out how they did with respect to the groups, and also then to be able to fairly compare their times to each other? And the answer here would be that you would need the mean and the standard deviation of performance time for each group. Luckily, they did have that information. The finishing times for the men ages 30 to 34 was 4,313 with standard deviation of 583, and the finishing times for women ages 25 to 29 group has a mean of 5,261 seconds with a standard deviation of 807 seconds. The distribution of finishing times for both groups are approximately normal. So if you watched my video lectures, you have the 3 pieces of information that you need to make raw scores that come from distributions of different means and standard deviations comparable, right? Remember, this is a bit confusing here. A better performance score corresponds to a faster finish, so lower number of seconds. So if you're in the lower end of the distribution, that means you're performing better. That's different from the logic of SAT scores, that if you're in the lower end of the distribution, you're not doing very good. All right, clearly, both performed above the mean of their own group. But which one deviated relatively less from the mean and performed better. Because remember, performing above the mean in this case, it's performing in more time, and that means worse, right? I can't compute these deviations in seconds. As you might imagine, a deviation of 10 seconds from a mean of 100 seconds is likely more significant than a deviation of 10 seconds if the mean is 1,000. In sum, it is useful to compare raw, it's not useful to compare raw scores. So what I mean here is that it's not, it's not a matter of just looking at the number of seconds that Leo completed the race with and just subtract from the mean score and just use that difference and do the same for Mary, because both would be in seconds. And then, like I said, it's raw. What does that mean in the context of each distribution? So we need to do something different, and you probably know what it is that you need to do if you watched the class, the lecture videos. So let's do that. I'm fixing things as I go along here. Question 2. Compute the performance z-score for Mary and Leo and interpret the results. Who did better and why? So I'm giving you a hint here of what the z-score formula, and I would pause the video and give it a shot before you watch the results here. So what I would do, if you're ready for the answer, I will get the z-score for, let's say, for Leo first, and that will be the score that Leo got, which is 4,900, blah, 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 minus the mean score for his group, which is this thing. The subtraction needs to be done first, so that's priority. So I need to put parentheses, and I'll divide that by the standard deviation of that group. And then for me to be able to see that result, I'll just tell R to print. Then I'll do the same for Z, Mary. Except now I'll use her values. So she was a bit slower than him. That's her race time. But her group is also, in general, slower. So here it is. And that's the standard deviation right there. And I'll run, and once you print, we can see that Leo scored, or the time that Leo took to race was 1.09 standard deviations above the mean of his group, and that's a bad thing because slower is worse. And Mary is just a tad bit above average, so she would have ranked better, right, than Leo within her group compared to how he ranked in his group. But let's look at the rankings properly. Rankings have to do with, you should be thinking percentile, right? So z-score expresses how many standard deviations above the mean a particular score is. Results show that Leo is 1.08 standard deviations above the mean, and that Mary is 0.31 standard deviations above the mean, and thus Mary took longer to complete the race than Leo in absolute terms, but she did better with respect to her own group. Given that it was a race, she would have obtained a better position, right, in that race. To confirm what I just said, we can actually compute the rankings of each one of them within their respective groups by computing the percent of athletes that did better, had lower times than Leo, and the percent of triathletes that did better than Mary. We expect the latter to be smaller than the former, right? Less athletes did better than Mary than Leo. So we expect Mary to be in the lower percentile, because that's a reflection of goodness in this situation, than Leo. Recall that the function p-norm takes as input the score and the mean and standard deviation of the benchmark distribution, and outputs by default the percentile, the area on the lower end of the curve. we can do this in two ways. We can use ROI-scores, and let's do Leo first. And here I'm writing, just the name of the object that will store the percentile, percent better than Leo. And that's the function, pnorm, that gives me the probability, the percentile, as we saw in the video lecture. Here is Leo's score. Here is the mean score, the mean time of people in his race group, and that's the standard deviation of people, the distribution in his group. And we want the lower tail because we want the percentile. So we want whoever the probability of getting this time or lower. So we'll run this. We have 0.86. So he's in the 86th percentile. Being in the higher percentile in this case, again, means worse, because higher time is worse time, worse performance. So Leo did worse than, his time was higher than 86% of athletes in the male group. Now you find the percentile for Mary. Don't look at the results, go try it out, and then come back for the solution. So if you look here, I'm doing the exact same thing. I could copy and paste this piece here, and all I'm changing is the name of the object that will store Mary's percentile. It's percentile better than Mary. And we'll use pnorm. That's her score. That's the mean of her, the distribution of her group, and the standard deviation of the distribution of her group. And again, I want the lower tail because I want percentile. So if we run, we see that her percentile is the 62nd percentile. So better than the 86th. So Mary did worse than, her time was higher than 62% of the athletes in the female group. So in the female group. Let me release this. Thus, Mary would be better ranked in a race with her performance within her own group than Leo within his group, right? So I said we can compute percentiles in two ways. One, I'm using the ROI-scores, and because I'm using the ROI-scores, I have to use the mean and standard deviation of the actual raw distribution. But I can do that using z-scores. I know the z-score for both Leo and Mary because I just computed them. So I can use the same pnorm function, except I'll use the standardized normal distribution that has a mean of 0 and a standard deviation of 1, and then I can use the standardized score here. And if you run this, you see that we get the exact same probability. So it's just easier because then it's just one parameter that you would have to vary. Once you have the z-score, you just use it and you don't have to go back and forth like getting the mean and standard deviation of the raw distribution because you're not using the ROI-score, you're using the z-score. And here you can do the same for Mary, and just to check, you can see here that she's in the 62nd percentile, just the same. So same results, just a bit simpler, because you can always use the same parameters to specify the distribution. That's why z-scores are comparable, because they're sort of referring to the same distribution. When you shared your results with your friends, Leo was disappointed and felt challenged. He asked you what would be the performance time he would need to reach to tie with Mary, right? So he became competitive there. So like, what? She's doing better than me. So what is that performance time that I should reach if I were to be tying with Mary? So in this case, we have the percentile, but we want the score back. And for that, we use the qnorm function, right? So here we are saying target time for Leo. We use the qnorm function. We provide the percentile of interest and then the mean and standard deviation of Leo's group to see what would be the score to put him in the same percentile as Mary in that group. So if we run this, we get the performance time. We'll continue with the guided activity in the next.